underneath, right? So what we do is we build a separate 3.5 on silicon wafer, and there's a lot of research and all the stuff that goes into this. The research problems are different than if you think you're building components. And we then transfer the CMOS through wafer bonding. So this is 200 millimeter. We actually take the CMOS off of the original foundry wafer, and we put it on top of the 3.5 silicon wafer. And so what's really cool about that, now inside SMART, you can, in the design kit, where we left space for 3.5 device, we cut a hole in it, we process 3.5 device, and then we bring tungsten plugs up, so it's the same level as the silicon source drain. The reason that's important, because remember, it's got to go back to the foundry and look like it never left their own front end, right? So then when it goes back to the foundry, metal 1, remember, is tungsten plugs come down to touch all the silicon devices, right? So they touch the silicon devices, but sometimes they touch what they think is a silicon device, but it's actually a tungsten plug that goes down to a 3.5 device. But the 3.5 device is never exposed up to the surface, right? So in this way, we just made everything we do opaque to the foundry, right? The foundry still, we buy actually a front end and a back end from the foundry, which is another interesting thing, because I'm a customer to the foundry, right? I'm not trying to like push my technology to the foundry, I'm a customer, right? I just put my own technology into my wafer, right? So this is what it kind of looks like. The regular flow is you take a silicon wafer, I go to a silicon foundry, and then I do the back end, that's for the front end, then I do the back end, and then I get a final chip. Here we make a separate 3.5 on silicon wafer, I merge them with this double transfer, process the 3.5 devices, finish them in the foundry, right? So this allows us to do things like this. This is a Global Foundries 0.18 micron CMOS that's sitting on top of a indium gallium phosphide red LED. We're going to make LED arrays out of this on top of a silicon substrate. These are just buffer layers, and so like in this process over here, we'll come along and dig a hole down and then process this 3.5 device and interconnect it. So what's interesting now is because of that implementation constraint that we put at the beginning through our innovation process, we now have something, and we didn't really plan this, right? Again, it's hard not to do the linear thing, right? But all of a sudden we start realizing we're like a silicon IC company. Silicon, right? And so we're in this process where we take the Foundry Design Kit, right? We didn't have to make it already exists. But for the 3.5 devices we're adding, we add our own device models into this PDK, right? That was interesting, by the way, because I had to get people to do models for 3.5 devices academically to actually make them go into the PDK, which means there's a lot of engineering work, but most of them didn't want to do, right? So but I have this, all of a sudden, new design gets proprietary to me, right? And then we get the front end, we do the 3.5 part, it goes to the back end, and then we get it back, we test it, and then we can make a new design kit. That's exactly how silicon proceeded. That's exactly how silicon technology goes. So when I was in grad school, we were always dreaming of, well, how is this all going to work? How could you eventually get 3.5 devices into a real silicon chip, right? And so here it is. This is the test chip that we're operating. Now notice how there's multiple 3.5 technologies. Again, something we discovered was that during the development process that we could develop one test chip with all the technologies in them, and when it comes out of the front end, it's the wafer that we attach to the CMOS that determines which part of this test chip is operating. So in other words, if I attach a gallium nitride hemp silicon wafer, only the circuits in the GaN hemp area is going to work. But see, that gives us a huge parallelism. We can develop four design kits with one foundry run, right? Because if I have 24 wafers, I can attach 7 of one kind of wafer, 7, right? So then I have all these design kits that come out, right? So this is kind of a cool thing. One of the hot areas that we didn't anticipate, remember that innovation process showed you, changes with time, right? So you have to take in new effects that come in. That's why it's a dynamic process. One of the new things that came in that we didn't see was we thought that this market would be the last one because it's white space. Right now silicon can't make any contribution to photonic space, right? It doesn't have that capability. A silicon foundry can't make things that emit light, right? So we thought this would be later, but to our surprise, this has become a super hot area, and there's lots of interest where, you know, the ability to drive LEDs and CMOS in the same chip. So a silicon chip pops out as a lighting chip, right? And what's funny is that once you start to design in the same platform, you change design. So these designs are put out because things are normally separate chips. It turns out, of course, when you integrate them, you get new innovation. You realize, why are we doing it this way? Right? Which is what you really want, because that's new innovation, right? So that's led to all of a sudden us realizing, well, we can now make an enterprise, because what have we just created? We realized that we have an Intel, but it has no manufacturing infrastructure. Something I didn't tell you, that all those processes that we're doing in Lees, smart Lees, we now found external vendors for them. So we have multiple proprietary processes, but we could design innovative ICs and use foundry wafers, but no one else can have access to technology unless we license it, right? So it's kind of, and you think about it, this is where the industry had to go, because you eventually had to get a high return on capital. And so if you have a proprietary chip company, which is just like Intel, but it never has to build fabs, you now are back on a capital return trajectory like the early silicon days, right? So it makes sense that the industry had to get here. We use partners to scale, like we were just saying. The cool thing is it's totally, we have real intellectual property. The other thing, you can never copy it. Today in Silicon World, if you get a GDS file or something's running in a foundry, you know, preventing intellectual property from leaking is like impossible. Here, there's like steps that no one else sees, right, that are outside the foundry thing, so it's impossible to copy, right? So you got IP protection, it's commercially viable, and I really do think that over time, this is what the industry looks like. So I will end there. Sorry for going later, even that took a little bit longer than I expected, but our original tagline was enabling the integrated circuits of the future, but with, any people here from the US know the current political climate, we now have a new tagline, which is, we're trying to make silicon great again. So I'll stop there and answer any questions you might have.
Okay, very exciting talk. So I'll open up the floor for some quick questions. All right, maybe I'll get started. How do you get the light out of your LED?
Very good. So there's some stuff that we're working on right now on that, but there's two options, right? It's either got to go up or it's got to go down, right? And we can do both.
Okay.
So just remember that. I mean, if you think about it, right, we're moving and transferring layers like crazy, right? So the only thing you have to do to get the light out to the bottom is to replace the silicon substrate, right?
Mm.
So that's one process.
Okay. Any questions from the audience? One here.
I'm one of the students who is studying the digital leadership. Digital leadership. Yeah.
Digital leadership.
Yeah, digital leadership in the college. And then I quite like the part that you are talking about is how market application, technology, and implementation can put together. And then I'm sure you have a lot of experience from MIT, which is from academia, and also you try to move your innovation from academia to the market, and with some of the investors who is going to pay money to you to work on some innovation. So how to break these barriers of the expectations of the market or the expectation of the investors?
You know, expectation management along the whole way is an issue, because even on the R&D side, you know, I mentioned the unalignment current demands on researchers versus real innovation, right? So we've completely destroyed the value of publications. We're trying to destroy the value of patents, but useless patents just don't go anywhere, so that one kind of self-compensates. So I would argue that the entire thing is managing expectations between different kinds of investors. So at the R&D level, trying to tell people that, this is more important than. Yeah, and so, one question is, why am I in Singapore? Right? So what I think that happens is, I always said this, that innovators will move to where they have to go to make it happen. And so as the R&D infrastructure in the US changes, that's true everywhere in the world. I'm kind of like moving ahead of this sort of collapse of what people think about, right? And so I'm just like one step ahead, moving as it becomes impossible to do what I was doing before in the last stage, right?
So moving yourself closer to the market, right?
But what I'm saying is I can control the expectations because I'm ahead of the collapse of the worldwide innovation ecosystem, right? So I didn't have to deal with what young professors are dealing with today, which is that, for them to do what I was doing is almost impossible, right? So, there's multiple things going on here, but even